Thank you very much to the organizers for inviting me to speak at this very impressive conference. I'm very pleased to be here. And, well, the word absolute probably makes you think of set theory. And those who know me also perhaps will think of set theory. Now, like many people who spoke at this conference, I was influenced in my mathematical development by the school of Paul Erdős. And for me, combinatorics and set theory basically are the same thing, infinite combinatorics. And well, let me say I'm in good company. Today, we had a very nice talk which mentioned Elikesh. And just as a nice memory of this person, let me just say that his first paper was in set theory. He wrote his first paper with Erdős and Heinel on infinite combinatorics. And it was about partitioning subsets of kappa and finding homogeneous delta systems. But don't worry, if you are not in set theory, you don't need to know absolutely any set theory for my talk. It's not going to be about technical notions, and I'll explain everything that I need. And what I'm trying to do in this talk is to remind you of a deep and interesting connection that set theory and model theory have had. And also some recent developments that show that that notion is perhaps is worthwhile considering again. So let me start by explaining what I mean by absoluteness. Absoluteness can be defined between any two models of anything. We'll mostly mean absoluteness between various models of set theory. Set theory for us is ZFC or some weaker versions of ZFC, or stronger, depending on the context. So in particular, if you look at a sentence, some sentence phi, it's absolute if its truth value does not change between these models. And we'll talk about forcing extensions. So let us say for the moment it's absolute if it cannot be changed by forcing. And the notion is absolute if its value doesn't change in various models. So what I'll do first is to remind you of some notions that are absolute between models of set theory and some that are not. So we'll mostly be interested in absoluteness between forcing extensions, and these are made on transitive models of ZFC. And so what happens is that, or ZF, is that the property of being an ordinal is absolute. That's important for us. And as I said, even though the word forcing is going to be mentioned many times in the talk, no knowledge of it is needed. I'll tell you everything you need. So examples of absolute notions. Well, to tell you the examples, I should first say in which context I'm working. So I'm working in the context of the language of set theory for the moment, which is just a very simple language, just has one binary relation for the membership. And we will be talking about formulas that can be written in this language. So a delta zero formula is a formula which is almost quantified free in the sense that all the quantifiers that appear in this formula are bounded by a set. And such formulas are absolute. Then there are many more complex formulas which are absolute. And in particular, there is this very nice absoluteness theorem which applies between any model V of ZFC and the constructible universe L. It is Schoenfeld's absoluteness theorem. And it says that pi12 and sigma12 sentences of analytical hierarchy are absolute. So using these tricks and similar tricks, we get that many notions are absolute. The membership, the equality, the subset relation, the first infinite cardinal, Aleph 0, being a function, any sentence of the piano arithmetic, sigma 1,3 consequences of the axiom of choice, the Riemann hypothesis, the truth value of P equal NP, and many other things. Things that are not absolute are being countable, being a cardinal, being aleph 1 being the first uncountable cardinal, the size of P of omega, none of these are absolute. So when we say that aleph 1 is not absolute, that shows you why in set theory we like to use different notation here. So this is aleph 0 considered as an ordinal, omega. This is aleph 0 considered as a cardinal. And it happens that this equation is always true. The first infinite cardinal is exactly omega. But then the first uncountable cardinal may change its ordinal value because of the lack of absoluteness. Okay, so let's see what kind of things we can add by forcing. So the concept of forcing is you have some universe of set theory called V, and you extend it to a bigger universe, V of G, which will have some more objects. So what you could add in such a process, even if it didn't exist in V, is, for example, a new function from omega to 2. So this is like a subset of omega, or you can add many of them, and in this way you can violate CH. So this is the first forcing construction that was ever made in 1963. Or you could add a new branch to a tree. So you could add new, so this, I should say that this, of course, was done by Cohen. And that's how forcing was invented. You could add a new branch to a tree, for example, to a tree of height omega 1 of V. And, for example, you could kill a Suslin tree. That's a popular construction, also very old. Or you could add a surjection from omega to what used to be omega 1. So in that way, omega 1 is no longer going to be uncountable, so you will have to change omega 1. The new omega 1 will have to be bigger. So we call this collapsing omega 1. So these are all very old and natural forcing notions. And what does this do for model theory? Well, these observations that you can add many objects, simple objects, make it natural to ask if notions in model theory are absolute. For example, can we make two models isomorphic if they were not isomorphic before? That's a very natural question. And this is the kind of questions that people, of course, asked as soon as forcing was invented, especially since at the time the model-theoretic and set-theoretic community were very close to each other and had a large intersection. Or can we change the fact that some kind of nice model exists? By that we might mean saturated or universal model. So let us read something on this from a book that I like very much. It's a book which is quite old, from 1972, written by Gerald Sachs. It's called Saturated Model Theory. And, well, he is also known as the inventor of Sachs forcing. But it's interesting when you read from what he wrote, you wouldn't think that he actually liked set theory that much. So he says that model theory bears a disheartening resemblance to set theory, a fascinating branch of mathematics, but with little to say about fundamental logical questions, and in particular to the arithmetic of cardinals and ordinals. But the resemblance is more of manners than of ideas, because the central notions of model theory are absolute. And absoluteness, unlike cardinality, is a logical concept. That is why model theory does not founder on that rock of undecidability, the generalized continuum hypothesis, and why the Walsh conjecture is decidable. Let me tell you what Walsh conjecture was, because we know it mostly in the past time. We know it more by the name of Morley's theorem. So Morley answered Walsh conjecture in 1965 by showing this very beautiful theorem that a theory, for me it will be a countable first order complete theory, is categorical in some uncountable power if it's categorical in every uncountable power. Categorical means it has just one model up to isomorphism. And it follows immediately that being uncountably categorical is absolute. Why is this? Well, that's because our forcing notions are sets. And since they are sets, they're not going to change the whole universe of set theory. So there will be some cardinal kappa above which the forcing will do nothing. So in particular, such a kappa, the theory will be categorical. And therefore, by Morley's theorem, it will be categorical in every power. So, by the way, Morley should have been mentioned yesterday with the connection with stability. Somebody else was talking about stability and said that Shelah invented stability. That's not the case. Morley invented stability, as far as I know, and it appears in the work on this. So Morley, there is a large debt to Morley in model theory, and also the classification theory of Shelah started by this theorem and trying to generalize this theorem. So let us move on then to also say that Morley was motivated, actually was working with a notion of rank. And although more perhaps simpler proofs of Morley's theorem exist, the first proof was given by a notion of rank, which is actually a topological notion based on Cantor-Bendix's derivative. I'm mentioning this because at the end of this talk, I will come to some newer research involving topology of formulas. Well, I'm not going to say anything about Morley's rank, but in fact, Morley's rank and other kinds of ranks is the real reason why model-theoretic notions are absolute, because these ranks are absolute. And these ranks provide an absolute way to handle formulas. And now let us explain that a little bit. So semantic versus syntactic. So semantic approach to model theory studies the meaning, which are the models. Syntactic approach studies the formulas. And Morley's theorem and the huge amount of work that was done by Shelah and others after him is based upon a philosophy of connecting semantic notions with syntactic notions. For example, the number of pairwise non-isomorphic models of a theory is a semantic notion. It talks about models. And when you look at that notion, you wouldn't have any reason to think that it will be in any sense absolute, even in the categorical case. But it turns out that this semantic notion is connected with the syntactic notion. So Morley rank is a syntactic notion. It talks about formulas. And as I said, his original proof was based upon an analysis of such a rank. And when you're talking in first-order theories, syntactic notions tend to be absolute because of the compactness theorem. We'll see an example of that. So although we will not talk about Morley's rank, let us give an example of a syntactic notion which will be relevant to us and show why it is absolute. So to introduce this syntactic notion, I will also go into something that's important, which are saturated models. So saturated models satisfy all possible types of a given size. So a model of a theory T is kappa saturated if it realizes all consistent types of theory T which have size less than kappa. So it is easy to see that in this context that we have here, kappa saturated models are unique up to the cardinality. So there can only be one in a given cardinality up to isomorphism. This is known as the uniqueness theorem. And using the compactness theorem, we can prove that for every lambda, which is
saturated in its own cardinality.
Of size kappa. So we're just talking about kappa saturated models, so of size kappa. That's what it means, saturated. Yeah. So using the compactness theorem, we can prove that for every lambda with lambda equal to lambda less than kappa, there is a kappa saturated model, I should have said, of size lambda. I've forgotten to write that. So let us then see this syntactic notion, which is actually defined using a saturated model. So this is kind of a typical way that people define notions in model theory. They move between saturated model and the theory. And the point is that because of the properties of, like the one that we're going to use, do not depend on the particular saturated model, then we fix any such model which has large enough cardinality is highly saturated. And we called it monster model. So here is the property that I want to talk about. That's called SOP2. It says that a theory has SOP2 if there is a formula which exemplifies this property in the monster model. So what that means is that in this fixed monster model, you can find witnesses for this formula. The witnesses look like a tree, the binary tree. And along every branch of this binary tree, the formula phi x bar with the parameter a with the nth initial segment of the branch. When you do that for all the n's, you have an infinite set of formulas, and this is consistent. Yet when you look along any level, or any two incomparable elements, mu and nu of the binary tree, when you try to satisfy the formula on both of those parameters, you'll get inconsistency. So this looks just like a binary tree. And now observe that this kind of thing is absolute. And properties like this one, but not yet this particular one, have been shown to be equivalent to semantic notions. And that's through the work in classification theory. So for example, something that everybody knows, order properties, even a weak one like this one, imply the maximal possible number of non-isomorphic models at large enough cardinals. So this is a consequence of the main gap theorem. Now, what can we say about this one? We shall consider a semantic notion which is connected with this SOP2. And it's the Kiesler order. I'm sure that Marianti will tell us more about this, but there will be here something about Marianti's own work. So the Kiesler order is defined in the following way. You fix a cardinal lambda, and you want to order theories using this cardinal. And what you define this is that the theory T0 is less than T1 if whenever you take two models of the theories, M0 and M1, and you take a regular ultrafilter over lambda. I'll tell you in a minute what regular means. Then, if you manage to prove that the ultra power of M1 over this ultrafilter is lambda plus saturated, then it immediately implies that the ultra power of M0 is saturated. So the idea is that T0 is less than T1 if T1 is is harder to saturate than T0. And the point of why we need a regular ultrafilter is that this order doesn't depend on the model that you have chosen. This is a theorem of Kiesler. Regular ultrafilter, well, the definition is not important, but it just means that if it is an ultrafilter on lambda, then it means there is a family of lambda many elements of the ultrafilter such that then every infinite subfamily has empty intersection. So Kiesler defined this order. And you can also say T0 is less than T1 if for all lambda we have T0 is less than lambda T1. It was introduced in the 1960s and was used by him and Schellach to complement the classification theory offered by stability. In particular, Kiesler proved that having the strict order property implies that the theory is maximal in this order. And note that there is no reason to believe that such a thing should be absolute, because it's totally semantic. So the existence of ultrafilters, of ultrapowers, their properties, we should have no reason to believe that this is absolute. Now, the paper that I mentioned just before, in this paper by Marianti and Saron-Scheller in 2013, they had a completely original idea. They continued a long list of people who tried to solve this problem, but they actually solved it. And they showed that being SOP2 actually suffices for maximality in Kistler's order. And what is really interesting about this is that in this same paper, and using the same circle of ideas, they showed that a certain equality holds, a quality between two cardinal invariants, which answered the question that Hausdorff asked in 1936. These are two invariants of the continuum P and T. And although we do not necessarily need to know what these invariants are, let me say that there is a list of at least 50 different cardinal invariants of the continuum that we know, and each two of them, apart from these two, were shown to be independent of each other by forcing methods in the 80s or so. And this one was a puzzle, and we now know why it was a puzzle, because it actually is not an independent inequality, it's an absolute statement. So you see here that model theory brought absoluteness to set theory. Well, so to wrap this up, this equality is absolute because it is connected with the SOP2, which is absolute. So let us now talk a little bit about interpretability and ask ourselves, how about the converse to this Malliares-Scheller result? So if a theory T is maximum in Kistler's order, does it imply immediately that the theory has SOP2? So this would actually give us an equivalence between a semantic and a syntactic notion, and would prove the maximality in Kistler's order absolute. So the conjecture is that this is true, but the question is open. And as far as I know, the best partial results is offered by some papers, two papers, one by Scheller and myself in 2004, and the other paper by Scheller and Usvetsov in 2008. And now we're going to explain a little bit what these papers offer. So this work concerns another order, interpretability order, which is again defined using ultrapowers, and which has the property that a theory which is maximal in this particular order is also maximal in Kistler's order. I'm not going to give you the definition of this order. But here is the theorem that one can, that comes from this work, that a theory is maximal in this order if a theory is maximal in this order in some model of GCH, then the theory has SOP2. So that's very interesting, because the antecedent is a set-theoretic notion which depends on a model. The conclusion does not depend on a model. Having an SOP2 is an absolute notion. So this leaves open two questions. A relatively minor question, modulo what's known, is the connection between this order, or the maximality in Kistler's order, and the maximality in the interpretability order. And I say relative to what is known because there is a very nice recent paper by Malliares and Scheller in which they have studied this connection. And, well, it was studied a little bit before, and all indications are that these two things are the same. But there is a major question if GCH is necessary. And it is not likely, well, perhaps there are people who will do it, but it has been tried to change this proof and to remove GCH, but it's not likely that that's how it's going to happen. But if we manage to prove set theoretically by some method that GCH was not necessary, then we'll have a confirmation of it by this model theoretical notion, which is absolute, and vice versa. So Let me now move to some things where semantic and syntactic do not agree so well. So I have stressed throughout this survey that the equivalence between semantic and syntactic depends on notions from first-order model theory. It looks like a miracle, although one may avoid it by only studying formulas and forgetting that one is working in this context. But actually, this is a miracle. Much of it depends on the compactness and completeness of the first-order logic, and this is something that is quite unique to the first-order logic. And let us now go through some examples of absoluteness and non-absoluteness in general model theory, and finish out by pointing perhaps a possible example which is true, might be pleasing, something from my current work. So let us start by contradicting Sachs. So Sachs said that GCH and model theory, luckily, as he says, have nothing to do with each other. So let's see if that's true. Let us find GCH within the first-order model theory. So here is a semantic notion of the universal model. A model of a theory is universal if and only if it has the property that embeds all the other models of the theory in the same power. And saturated models are universal, and special models are universal. So under GCH, every countable first-order theory has a universal model in every uncountable power. But the interesting thing is what happens without GCH. So this is the fact that I've just said. If you have lambda to the less than lambda is lambda, then T has a universal model in lambda if lambda is uncountable. So our idea has been, in a long list of work, to classify theories by the class of cardinals for which there is a universal model at T independently of this value, of the value lambda to less than lambda. And this work has a very long history involving Schelach, Grossberg, Koijman, myself, and many others. And what I would like to say is that there is a very beautiful recent theorem by Schelach which achieves a crowning point to this program, which shows that there is a countable first-order theory, T star, such that T star is the worst possible. It has a universal model in lambda if and only if lambda to the less than lambda is equal to lambda. So GCH for uncountable cardinals is exactly the statement T star has a universal model in every lambda. So we can say GCH in a model-theoretic way, even using first-order model theory. Now let us move a little bit to other kinds of model theory. Let us consider the logic L omega 1 omega. It's a logic which is like the first-order logic, but you can have infinite conjunctions. It's not compact, because you can define well order in this. And however, it is complete by a proof by Karol Karp from 1964. And here is a nice question. Suppose that tau is some countable vocabulary and phi is an L omega 1 omega sentence. Is the statement that phi has an uncountable model absolute? So it's a natural question, and you would think that by the completeness of the theory, this might be a solvable question. So recall that in the first-order logic, this kind of question is answered by the Löwenheim's column theorem, which implies that having any infinite model is equivalent to having models of any infinite cardinality. And having a countable model is absolute. So here, however, this is not going to help because we do not have a Löwenheim's column theorem. It exists downwards for complete theories, but not for sentences. So let me show you how this question was solved. Oops. So this question was, the answer to this question came from an unexpected direction. The idea of this answer came from a paper by an idea of Paul Larsson in 2013. And this idea used set theory. And this and more general results appear in a joint paper by Baldwin, Larsson, and Schellach from 2015. And they also talk about the logic L omega 1 omega of Q, which is the same as L omega 1 omega, but Q is the quantifier which says there exist uncountably many. So let me sketch their proof just to show you how a sophisticated approach in set theory can be used here. So let us take a sentence in L omega 1 omega for which it is consistent that it has an uncountable model. So we know that somewhere in some universe of set theory it has an uncountable model. Now there is some encoding technique of Schellach which helps us to state this statement in a small fragment of ZFC with parameters. Let us call it ZFC star. And this now satisfies the downward Lowenheim's column theorem. So we can find the countable models of this, which contains our language and satisfies that our sentence has an uncountable model. So now comes the idea of Larsson. You know, if we were in first order theory, we would just now take an elementary extension, but phi is a conjunction of possibly countably many things. So that's not so easy. So, but however, it can be done. It can be done in a highly non-trivial way using non-stationary Tauer forcing. So using this forcing, we construct an uncountable model, which is an elementary extension of A, and such that A is correct about uncountability. That means this model, it's not a model in V, but everything that it knows about uncountability is actually true in our ground model. So in particular, if you take the model of the sentence in this model, it's actually in the ground model where we live, an uncountable model of the sentence. So this means that if it is consistent to have such an uncountable model must exist in the ground model. So let me make some connections of this with the favorite question of model theory. So it was asked in 1996. The question is the complex field with exponentiation quasi-minimal? This means that every definable subset of this is either countable or co-countable. And I think you know much about the history of this very nice problem, which connects with the work on O-minimality done by Wilke, etc. So many excellent mathematicians have been working on this problem. First, Wilke and Zilber, and then here in this audience, several Bayes, Kirby, Mantova, and others, and they all trying to get a yes or no answer. So this would be an absolute answer. And let me say that it is not known even if the reals are definable in this context. So if the reals were to be definable, of course, we would have a negative answer. But that is not even known. So from what I asked Alex and Udi and others, Jonathan, there is no really reason to think that this will be absolute or not. It's simply not known. OK, the question resists. And, well, you know, being the devil's advocate and having seen many absoluteness and non-absoluteness results in my life, I ask, well, is this maybe that these people are working on something that's impossible to solve because it's simply not absolute? And let me say, for example, an association of similar results that one has in set theory. So there was this Borel conjecture about strong measure zero sets. So strong measure zero sets are defined by some countable conjunction. In analysis, they have measure zero, but they are stronger. And Borel conjectured that maybe all of them are countable. And actually, it is possible that all of them are countable, but it's also possible that it is not. So if you think of Borel sets of measure 0 and the opposite of Borel sets of measure 1, it does look a little bit like, you know, this quasi-minimal context. So it asks the question, is the answer to Zilber's weak quasi-minimality conjecture, which this conjecture is known as, or this question, is it absolute? So I was interested by this and started working on it, and the work in progress shows that by a technique similar to the one by Larson, I believe that this question is actually absolute. So this uses Zilber's axioms, and in particular Jonathan's work on presentation of these axioms in a different way, in which there is one axiom which uses L omega 1 omega of Q. Well, as I say, this is in progress. Perhaps mistakes will be found, but at least I am pleased to say that it looks like this actually is an absolute question. Okay, well, let me now mention some work which goes in a different direction of model theory. All what I have said so far. Yes?
When you say it's absolute, you mean just with respect to forcing extension? Or any kind?
Just with respect to forcing extensions. Yeah. So, yes.
And this weak quasi-minimality?
Yes, that's weak quasi-minimality. The strong quasi-minimality is that, well, there is some model and that it is the unique model of this theory. I'm sure Jonathan can tell you much more about it than I can. So let me move now to another part of model theory, which is not as combinatorial at first sight. So what we have been talking about is sort of connection between set theory and model theory, and absoluteness in the sense of set theory. But absoluteness appears in other concepts as well. Let me just remind you of something I said before, and sorry that this is a kind of linear. We cannot go back a few slides at a time, so I have to be clicking. When I defined this SOP2, just before that, I was talking about saturated models. Really, somebody should invent this, right? Is there some button?
On the left.
On the left, right? That's what I'm. Oh, you pressed it more than once, or what? Okay, I'll arrive. Okay. I just have one more slide, guys, you know, so just be patient. Usually they tell you that at the end, but unfortunately I'm not yet at the end. So here it is. This is something that was defined modulo a saturated model. And we said in a previous slide that it doesn't matter which saturated model we take because everything is the same in every saturated model. All saturated models are isomorphic. Well, they are, but only when we look at them as first-order structures. So if we want to talk about properties of saturated models which go beyond first order and involve notions that are not algebraic, but perhaps have some other mathematical flavor, we might lose this. And this is exactly something that happens in a very fascinating, so what do I do now, Artem? Artem, may I ask you to be my assistant? I've always wanted you to be my assistant. Please, thank you. We are very pleased at UEA to have had this young colleague coming from UCLA. Well, but he's doing as badly as I am, but thank you, Artem. It was a little bit quicker. Thank you. And he got the right slide as well. You can see we prepared this in advance. I want to talk to you about the work of Newelsky, Ludovic Newelsky and his group, including here some of his colleagues, actually both Krupinski and Simon are here. So this work concerns generalizing geometric model theory. So geometric model theory looks at notions from first-order model theory in terms of group actions. And well, this is a very big generalization, but the big idea is to consider not just the structure, but to consider some actions of groups on these structures. And of course, Laskar, Pillay, and others later have studied this, and Anand is a specialist in this. So this works really well, especially in the stable context. So what is interesting about this, maybe I should still go here to make it a bit easier to read and everything at one time. So suppose that you have some countable, complete first-order theory, and you have some unary predicate that defines a group in the saturated model. And the point is that actions of such a group may code many properties of forking and formulas. And it works really well, especially in those contexts where forking works well. So stable context, for example. So stable group theory is a central notion in geometric model theory. Now, you might like to generalize this to unstable concept, and it has been done. There's a work of Artem and Simon with NIP theories, etc. But Newelski had a different idea, which used topological dynamics. So topological dynamics actually looks at topological actions. So there is some topology going on. And there is something called Alice semigroup, and the ideals on this Alice semigroup. I don't have to give you the definitions of this. I can send you to some very nice papers that exist on this. And in particular, there is a set of slides from Newelski when he first started talking about this in Mostovsky's 100 years old conference. The point is there is this topology, and topological notions in general are not first order. So the absoluteness and the independence of this saturated model now are no longer granted. So many properties that one might want to study in this a priori have no reason to be actually absolute. So one of the things, for example, you can look at the flows. So the flow is a, well, you look at the actions of a group on a topological space that defines the flow. And one of the kinds of flows that they look are the types consistent with the given model. And as I say, all of this might depend on the choice of the saturated model. And what I find quite surprising is that in many cases this is not true. It still is absolute. And here is this theorem from a paper by Krupinski, Newelski, and Simon in 2017, which says the following: if you'd have a definable subset X of a product of sorts, that may be sorts, they may be less than the size of the saturated model, the Alice group of the automorphism C flow of SXC is of bounded size. It means it has size less than the size of the saturated model, and it does not depend on the choice of the model. So that's quite a beautiful and, I think, for me, interesting, mathematically, obviously, but also philosophically, an interesting theorem, which somehow shows that absoluteness can be brought from model theory up. So in this talk, I have tried to show you that set theory and model theory have an interaction that goes both ways. You can bring some absoluteness from model theory to some other concepts, like to these topological concepts, or to the set-theoretic concept, as was done by Maliaris and Schellach. And you can also use set-theoretic methods to show some absoluteness in model theory by using some rather sophisticated set theory, as was done by Baldwin, Larson, and Schellach. So thank you very much.